Good afternoon. The topic of discussion today is digital system design using FPGAs. Okay. So the idea is to give you an overview how to design FPGA based system. Now first look at this diagram. Now in this diagram, what has not been shown, that the whole thing will be connected to either to a PC or to a CPU. Okay. Now, if you want to design without any PC, then this will be interfaced with a microcontroller or microprocessors. You must have seen here BPU is written here. So this BPU is nothing but a processing unit. Okay, this line should be connected to that, which has not been shown. Now here, let's say we want to design a board. In fact, we are discussing from the hardware design point of view. In the board, there will be 4 integrated circuit chips. One will be the microcontroller or microprocessor. Second one is the FPGA, which is to be interfaced. Then one CPLD. Another is a flash memory. Okay. Now let's see. We know the purpose of FPGA. But what is CPLD? Why we are using CPLD stands for Complex Programmable Logic Device. This will act as a controller. Now, controller for what purpose? Here, the controller will get some command from the CPU, which is a microcontroller or microprocessor. And this command will be executed by the CPLD. We'll discuss what are the commands and what are the things to be done. And here, flash memory. Here in the flash memory, basically EEPROM device. Here the bit streams are pre-stored. Okay. And these bit streams will be downloaded to the FPGA. So how this will be downloaded? So first, the CPU will give command to the CPLD for initiating the downloading of bit streams from the EEPROM to FPGA. So how this can be done? That's very important. How the bit streams will be downloaded. Now, let's see here some major pins in FPGA. At the top, there is a parallel bus. That is the data bus. Can you see the data bus? Which is connected from flash memory to the FPGA. Please respond, Can you see the lines?
Yes, sir.
So this is D0 to D7 means 8-bit data lines. So through this data bus, the data will be delivered from flash memory and that will be downloaded to FPGA one by one. So that is the bit stream. Now there is one line called chip select bar. You just look at the FPGA. In the left, most of the VLSI devices like memory, CPU, controller, they have some line pin called CS bar. Normally in the CPU, this CS bar is not there, but in the memory, controller, this kind of devices, you will find this chip select bar is there. So when chip select bar is low, then the chip will be selected. And if the chip is selected, then only any operation will be performed, not otherwise. It will be totally disabled. So to make the vertex, this FPGA chip enable, this CS bar should go to low. There are two signals. One is write bar, one is prog bar. A write bar is to write the data onto FPGA. That means the data D0 to D7 will be downloaded provided the chip select bar is low and write bar is low. It's a must. And there is a line called prog bar. The FPGA will work in two modes. One is the programming mode, another is in the execution mode. In the programming mode, when prog bar is low, then the chip will be under programmed. Means basically the bits will be downloaded, bit stream will be downloaded. When prog bar is high, then it is not in the programming mode, then it will be in the execution mode. And C clock is a configurable configuration clock that is for synchronization with other device and FPGA. So these are the major pins. Another is done and busy. Busy means when is being programmed, it will be busy. And when it will be over, then it will give the done signal, means is over. For an example, 1 byte has to be downloaded. Each time 1 byte is downloaded, once the download is complete for that byte, it will give a signal done to indicate that it has been done. And initiate, there is a signal called initiate, init. So this is connected to busy. So when the FPGA is busy, then it will send a signal, busy signal, means it is busy. And initiations, when it gives the init signal, that means any operations, downloading or anything can be initiated. So these are the major pins. And there are also some, look, you don't have to mug these things. These are M0, M1, M2. These are basically device specific for some FPGAs. Depending on this M0, M1, M2 signals, it will be in a different kind of configuration modes. That's not very important at this moment. So the pins what I have discussed for FPGA, major pins, do you have any question? Do you understand it? Please respond, don't keep mum. This.
Yes, sir.
Sir, can you please show the diagram once again, sir, please, sir?
The simple thing, the top lines are data bus. Then there is a done signal. When anything, each time a data is downloaded, then it will give a done signal
Sir,
1.
why the sir done signal is directly connected from the FPGA to the flash ROM?
No,
Why
no.
not to the CPLD?
While it is connected, that's immaterial. That I will be discussing when I will be discussing about CPLD. First, I am telling you, you understand what are the pins? What are the purpose of the pins? Done means?
Yes, sir.
Okay, it has been done. When a particular operation is being performed, means let's say download. Okay, so when the data is given to the data bus of FPGA, then that data will be loaded and write bar signal should be low. Any external device, when it will put write bar low, chip select bar low, and data in the data bus, then it will take some time to store this data, what is called the write time. So once that data loading, means writing, is complete, then it will give a signal done. Understand?
Yes, sir.
Okay. So first, look, step by step you go. First, try to understand what are the pin. Then we'll go for how these pins are connected. So these are the purpose of the pins. Do you have any questions on these purposes? Write bar means to write the data. let's
No,
say
sir, no question.
within the FPGA, there must be some memory. From the common sense, what is there? Like when the data through data bus are getting downloaded onto FPGA, what does it mean? That means there must be some storage area where this data will be downloaded. Okay. Now, if there is a memory, the memory needs what? To write data onto the memory, what you require? You require a write signal. The chip has to be selected and data in the data bus. If they are stored in the consecutive locations, if the data are stored in the consecutive locations, then there is no need of address bus. Inside there will be a counter. Counter will be initially reset to a location 0, and then one by one the data will be stored and counter will be incremented each time after storing each data. That's right.
Yes, sir.
Okay. Now the question is, from where from the data will come? The data will be coming from this EEPROM, where already this data have been pre-stored. Now what are these data? These are the bit streams. For an example, let me give you an example. Let's say this FPGA will be used for a communication applications. Okay. For communication applications, let's say we want this will act as a signal processing system. For signal processing, there are different functions. The functions could be FIR filter, IR filter, FFT, low pass filter, many things. Now what you could do when you design an FPGA based system, you have to follow certain steps. These are called the design steps in a systematic fashion. First step is for what purpose you are using it. You identify that. Okay, let's say you have identified that you are using for some signal processing functions. Now, signal processing functions, what are the basic functions in signal processing? General signal processing. FIR filter, IR filter, FFT, or discrete cosine transforms, etc. Now, any filter could be band pass or band stop or low pass or high pass. Whatever the filter you design, what are the basic building blocks? The FIR filters and all, or IR filters. Now, so once you have identified that, let's say you are trying to design a chip, and this is PSOC. PSOC means Programmable System on Chip. So it will do the FPGA will do the function of a PSOC. PSOC stands for Programmable System on Chip. So why? Because depending on your need, you can configure this FPGA to any particular hardware function. So once you have designed your FIR, IIR, FFT, etc., you can write the code in high-level hardware description language. There are many languages. These days, the most popular language which is coming up, that is System C. Earlier, it was Verilog, but in recent time, System C is becoming very popular, particularly in USA, in North America. System C is becoming very popular because it is very close to C. Now, once you write the code, then you can generate a bitstream file. Okay, using these CAD tools, you can do that. And from Xilinx, directly these CAD tools are available. And these are available at free of cost, the Xilinx design tools. So you write, let's say you have designed a FIR filter. You have got the machine codes and the bit streams, these bit streams will have a size, specific size. Then let's say you have designed IR, you have designed FFT, etc. Now those bit streams can be downloaded onto this flash memory by using EEPROM programmer or EEPROM programmer or flash memory programmer. You can do it. Now, once you download the bit streams, stream, they will have some specific area. So for each module, let's say for FIR module, let's say n number of bytes to be stored, n1 number of bytes to be stored. So if it starts from location 0, then 0 to location n-1, the bit stream for FIR will be stored. Similarly, from n1 to some other locations, some other bit streams will be stored. In that way, bit streams for various functions can be downloaded onto this flash memory, okay, prior to put it onto the circuit. Now, once these bit streams are downloaded, so for how to identify which bit stream is for what, identification mark is their starting address and how many number of bytes to be downloaded. For an example, let's say a FIR filter has been stored from location 0 to location n-1, and that means n-1 number of bytes have been stored for FIR. So depending on the command from the CPU, this CPLD will organize such that the bit stream will be stored one by one in byte form from the square PROM to FPGA. And once entire bit streams are over, then CPLD will send a signal, which is not shown here, a control signal to the CPU. Like CPU will get interrupted by the CPLD, and once it gets the interrupt, then it will understand that the bit streams have been downloaded. That means FPGA will start behaving like FIR filter. Once the task of FIR filter is over, then let's say if it needs to be configured to IR filter. So bit stream for IR filter will be downloaded and FPGA will behave like IR filter. So do you understand the concept now?
Yes, sir.
Anybody has any question? Now the question, if you understand this concept, then what is the task of the CPLD? Task of CPLD is to generate some control signals to square PROM and also to FPGA after getting the command that you download. So one thing, this interfacing circuit has not been shown. There will be a parallel port to this port or USB port through which a CPU will be connected to the CPLD. Now normally in your laboratory, these FPGA boards will be connected to your PC through an USB port. Okay, but normally for the design, if it is a complete self-sufficient board, then the CPLD through a parallel bus will be connected to the CPU. That's all. And one line will be connected to the interrupt line of the CPU. So let's say CPU has sent 1 byte, which indicates you program the FPGA. Once, let's say CPLD has got this command is simple. A 1-bit information can be sent by the CPU to the CPLD. If that bit is 1, then one function will be performed. If that bit is 0, another function. Or if it is 0, 0, nothing. 0, 1 means download the bit streams. 1, 0 means a command to execute. 1, 1 means nothing. So let's say this kind of command has been given by the CPU to the CPLD. Then CPLD will do what? Will send a CS bar signal low so that FPGA should be ready. Chip will be selected. It should send a write bar signal low. Once the write bar signal is low, some data will be downloaded. But what data? So that's why it will send the address to the memory. Now how it will get to know what address? Because the CPU has already sent the command you download. Along with that command, it must have sent the starting address and how many bytes to be transferred. Let's say how many bytes to be transferred. There are 2 registers within the CPLD, or two
Sir,
counters.
sorry, sir. Will you please repeat once again regarding the address location? Just I missed that part.
The starting address must be there, because for bit streams, there are different sets of bit stream, maybe for FIR, IR, etc. How to identify that?
Okay.
So starting address of the bit streams and how many bytes to be transferred. This starting address will be stored in a register within the CPLD, and that will be given by the CPU. Okay. So CPLD will do what? This start address you will send to the EEPROM. Then once it sends that address to the EEPROM, and OE bar has been sent low by the vertex. Okay, because it has not yet been done, so done signal is low. So OE bar is low, address has been given by CPLD. C bar is chip select bar is also low for the flash memory. Then the memory will do what? The contents of the memory given by the address, okay, which is given by the CPLD, then that data will be going to the FPGA, and that data will be downloaded. And again, this done signal will be low, high. So in that way, and then the CPLD, this address will be address plus 1. So again, the next data will be downloaded. In that way, one after one, the data will be downloaded until the byte count register is set to 0. Byte counter is what? How many data has to be transferred for a particular type of bit stream. That's all. It's okay?
Yes, sir.
Okay. Can you tell? I'm asking Anirudh, answer these questions.
Yes, sir.
CPLD will have two registers. What are the purpose of the registers?
Sir, the starting address and how many bits to be uploaded.
How many
Sir, these things
bytes?
to be.
How many bytes to be uploaded?
Yes, sir.
Okay.
So these things should be stored in CPLD.
Who will give that? This information will come from where?
Sir, from the sir, PC.
Here from the CPU. Okay.
Yes, sir. Yes, sir. From the CPU. Sir.
Okay.
Yes.
Normally, in fact, when you design the system, PC will not be there. For example, let's say FPGA is used in a high definition television. Okay. To operate that television, will you bring your PC?
No, sir.
It will be within that. What is the cost of a typical high definition televisions? Maybe 40,000 or something. And for that, will you buy a PC of 50,000 rupees? So it is a self-sufficient system. A CPU will be there. In the laboratory, you connect with the PC because you have purchased a board to do some experiments. Okay. That's why you interface with the PC. Normally, these things will be connected to a CPU. And these days, many FPGAs are available where within the FPGA chip, PC is also available. Okay. But in general, I'm telling you, so it will be connected with the PC. So what PC will give the information? What are the informations will be initiated by the PC to the CPLD?
Sir, the number of bits,
No,
number of bytes that should be
Before
uploaded.
first, the information is whether it will be it will be programming the FPGA or it will force the FPGA to execute that information. Right? Have you noticed
Yes, sir.
here? One line is there, prog signal, prog bar. When prog bar is low, then the FPGA is in the programmed mode. When prog bar is high, then FPGA is not in the program mode. That means it will be in the execution mode. Because FPGA can work in two modes. Unless it is programmed, can it do any execution?
No, sir.
So
No, sir.
first it needs to be programmed. Programmed means it needs to be configured. So different kinds of terms are used. Normally, in fact, the term configuration mostly we use in the industry. That means it needs to be programmed first. So unless the FPGA is programmed, it cannot do any work. So this programming task will be done by this CPLD. Means it will create the environment such that the bit streams in the form of bytes will be downloaded onto the flash memory to FPGA one by one. Clear? So when the CPU gives the information, the download means you program the FPGA. Along with that, it must have to send two sets of information. One is the start address of the bit streams, and second is how many bytes to be transferred. That is called byte count. So each time one byte is transferred and the byte count will be the previous value minus 1. So this process will be continued until the byte count goes to 0. So that is a thing of programming. And once it is over, then CPLD will send a signal 1 to the interrupt line of the CPU. Why? Because CPU will understand that this is over. Programming is done. Now, any questions up to this?
No.
Okay, unless you do the hardware design only using the board in the lab, you will never learn how to design the system. Okay, like in most of the undergraduate colleges under MacOut, you will see that microprocessor boards are given. You write some few lines of codes in machine code and just get happy if it works. That's not the thing. The system design, you must have to know the functioning of each and every chip, which you will get in the manual. You have to consult these manuals, where the pin configurations you have to understand, okay, in the manual. Timing diagrams, which is very important. Otherwise, there won't be any synchronizations unless you understand at what time what is happening. Then you have to place it, use a variable, then connect all these signals and test it. Then your complete design exercise will be done. So here, why I have used CPLD? Because if I don't use CPLD, then I have to use a lot of logic circuits. Okay, and I have to design a controller which will generate all these signals: write bar, prog bar, clock bar. Instead of that, simply these days the trend is to reduce the overall design time. To reduce the overall design time, why? Because the cost of the design will be decreased. Time will be decreased means the cost will be decreased. And if the design cost goes down, then you can sell at a lower cost. And if you can sell the product at a lower cost, the sellability of the product will be increased. And if the product is sold in the market, then your company will retain in the market, will float in the market, not otherwise. So that's very, very important. Now again, so what are the signals to be given by CPLD? So CPLD, once it gets the command from the CPU that you program, then CPLD will make the CS bar low to the FPGA, will send the write bar signal low, will send the clock signal low. Clock is directly connected. Some external clock generator circuit is there, and that clock is given to both of them so that the CPLD and FPGA are synchronized. Otherwise, it will be giving a write bar signal and FPGA will be working in its own, then it will not work. There will be a mismatch. So to match it, all the signals like will be respect to the clock. Clock is the reference. So that's why this clock is called configurable clock, configuration clock. In the left-hand side of the CPLD, What are the signals? Address lines are connected directly to the flash memory. Okay, and data bus is going directly from the flash memory to the FPGA. Down signal. So each time, what happens? The down signal goes low when the data is not yet downloaded. So once it is low, OE bar is low, CE bar is low, then square prom will be selected. So depending on the address given by the CPLD, that data in that address will be downloaded into this. Once it is being downloaded, then down signal. After downloading, this down signal initially will go high. Okay. So once it has been stored to the FPGA, then again the down signal will go low. That means it is ready for getting the next byte. By that time, the address has been incremented by 1, and a counter which holds the number of bytes to be transferred decreased by 1. So this process will be continued until the count is 0. That means the bit streams, all the bit streams for this particular functions have been downloaded. Then CPLD will do what? Will send a signal to the CPU. What is the need of that signal? That signal indicates that programming is done. So CPU understands that program is done. Programming is done means FPGA is now will behave like the hardware for that particular function. So then it can send a command to the CPLD, okay, that execute it. Then it will just, what it will do, program bar signal, it will make high. That means FPGA is not in the program mode. So once it is not in the program mode, then what it will do? It will in the execution mode. That means there are some input and outputs which are not shown in the FPGA. It will take the data from the input, will execute that task in the way FPGA executes it, like execution. So because it will deliver the output to the output port, in that way it works. Okay. Now, if you have any questions, please. Okay, tell me one thing. When the data is being downloaded from the square prom to this, then what will be the status of the down signal?
Sir, down signal will be 0.
If down signal is 0 and once it is over, okay, good. And once it is
Sir,
over,
down will be 1.
fine. So the configurable clock, prog, write bar, chip select bar of the FPGA, that is understood now. So in most of the FPGA, you have to consult the manual because slight variations will be there from, but the basic signals, these will be common, like chip select bar, write bar, program bar, configurable clock. Okay, so busy or these things will be there. When FPGA is busy, means is getting programmed, the busy line will be high, then busy line will be low, then again the next byte can be stored. In that way, the things will be done. Now, in fact, FPGAs are available which are working at a lower voltage also. Okay. So here. So done signal indicates the completion of the configurations. So you can consult the manual to go. Now, from this design point of view, if you have any questions, please. I'll go to the next sections. So initially the configuration process, this is for particular vertex one, the reset the configuration logic. So first some reset signal will be there. At the power of time, you reset it. Because if something is already downloaded, that needs to be, this is garbage, that has to be reset initially. These are the signals I have already told. So M0, M1, M2, these are for mode. It can work in various mode. For an example, let's say some for parallel processing, a number of FPGAs are connected in parallel. Then same data bus, let's say 2-3 FIR FPGAs will be working concurrently, the same FIR, but maybe on different data. Then the same thing parallelly can be connected to some more FPGAs, like same data bus can be connected to the data bus of the next FPGAs and all. Okay, in that way, using one CPLD and from the same EEPROM, a number of FPGAs can be programmed simultaneously. So FPGA design cycle, define a new project and enter the design using Verilog or VHDL or advanced HDL languages like System C. Design can also be entered using schematic diagrams. Now some tools are available also, like some CAD tools where you can draw the state diagram, and from the state diagram directly that will be translated to HDL language. I don't know whether you have it in your lab or not, but this is a very good tool now. These are available. Simply you design the state transition diagram. That diagram you draw, very simple. You don't have to write the logic and all these things. You don't have to write the program. So it will generate the program, the Verilog code. Now these are required to accelerate the programming time. That means the product development life cycle will be reduced largely. These are quite expensive tools, but in that way you can do some automation and requirement of number of people will be reduced. For the companies, it is very, very effective tool.
Sir, we are having this kind of facility, schematic diagram entry.
Sorry, I can't hear you. Just think some noise is coming. Please. Yes.
So actually, we are having this kind of facility, schematic diagram entry. This schematic diagram
It's not very clear. You know who is speaking? Can somebody else? Same question can be asked by somebody. Because some noise is coming. You know, I'm not in a position to hear clearly.
Okay.
Hello, who is saying that?
Sir, I am showing you.
Shobik.
Yes, sir.
But some noise is coming. Can you ask it from somebody else's mobile or computer? I don't know. Somehow some noise is coming. I'm not clear. You know, it's getting cut. Your voice. Okay, I'm saying once again, you listen it and then ask me the questions. What I'm saying is this design can be described by diagram. Okay, the tool will support that, like any state transition diagram, the sequential, if you design a sequential machine, then what you do, you draw a state transition diagram, what is known as the state diagram. Now, state diagram consists of what? Some circle and some arc. Like whenever there is a transition from one state to another state, then we define it by an arc. And we also define the name of the states. Like if there are 4 states, you can write 0, like let's say 0, 0, 0, 1, 1, 1, 1, 0 in that way, and then 0, 0. Then whenever there is a transition, it goes from one state to another state. So state transition, and also what will be the output, we indicate, we write. So in that way, you can draw the diagram. And once you draw it, then it will generate, it will translate to any hardware description language from the schematic diagram. Okay, that's what I said. Now, any question? Hello? Shovi, can you hear me?
Yes, sir.
Did you understand what I said?
Yes, sir. Yes, sir.
Okay. Then compile and simulate the design. Find and fix timing violations. Okay. So you get the power consumption estimates and perform synthesis. Next. Then download the design to target FPGA board. Now this is for when you are doing with the CPU is connected. Otherwise, what you have to do, you have to download the design to what? Why to download? Design means the bit stream. Why to download the design?
Sir, sir, we can download it direct from the CPU or in any EEPROM or
First,
flash.
before that, first, yeah, in the flash. So that means you have to program the flash memory. Programming the flash memory means, let's say when you have written the Verilog code or any VHDL code that is there in the computer, in the PC. Because initial system design you'll be doing using the PC. Okay, after synthesis and all are over, then a bitstream file will be generated. Okay, and that bitstreams can be downloaded. That means can be programmed to flash memory by flash programmer. Okay, using the flash programmer, you can program it. So this flash memory will be completely programmed. Once it is programmed, then you insert on the board. Similarly, CPLD, you take a CPLD chip using the Verilog or VHDL, you program it, test it, synthesize it, all this. Then again, this will be in the board and this. And so for designing the board, what you have to do? You have to do the PCB layout. Okay, using PCAD or OrCAD, this design automation tool, you can design the PCB, place order for PCB. Then once you get it, then you test it. Then bare-footed board, after getting it, to insert this and solder them using, like here, for testing you can do the solder at lab, but for manufacturing, bulk manufacturing, we do it using the web soldering machines. Some kind of die is prepared, and using those dies, automatically the chips are soldered. Okay. So I think if you can visit any standard company, manufacturing company of electronics, you can have a look at how these things in batch these things take place. The conveyor belts. Many people are they sit one after one in a pipeline fashion. Each of them, they perform their job, and finally these components are soldered. So this is the thing. So download the design, and then once the FPGA based design is verified, the program can be downloaded under FPGA chip. I've already told that. Design can be downloaded using parallel port, USB or Ethernet or JTAG port if the board is connected to the any CPU. So these are the design flow. First, design using RTL coding, then synthesis. Place and route you don't need to do, that will be done by this. So that's all about FPGA design. If you have any questions, please. Now, once we understand it, then in fact slowly we are going for designing an AD processor. AD processor means analog digital combined processor within a same chip. So one is the analog processing, another is the digital processing. Now the question, why do we require? Already I have discussed what are the reasons for using analog, what are the reasons for using digital. For neural network kind of applications, we have a lot of neurocomputations where the neural network circuitry will be implemented using multiplier, adder, threshold detector, etc. And these things can be done by the analog circuits. The reason being, the digital circuits are they will occupy more area compared to analog. For example, 16-bit multipliers. You can analyze the complexity of 16-bit multipliers, which can be done very easily. It can be implemented by analog circuits. But definitely, the precision is more in digital than analog. But for neural network computations, we don't need that kind of accuracy. Okay, when we go to that, we'll understand. But when you do the neural computations, we need digital processing as well. Why? For example, feature extractions, feature pattern recognitions. In the pattern recognitions, pattern will be, how it will be, pattern will be classified. Pattern will be identified by some features and all these things. And these are based on the signal processing, image processing. For a particular image, different features will be extracted. So here, the computation, lot of computations are required to extract the features. And this can be done, well done, by digital signal processing instead of analog. So these are required. Again, after extracting the features, let's say for convolution neural network, lot of computations will be required, which could be done by analog. So there we can use the analog computer. Now, again the question is, when we design the computing systems, we require a CPU, a memory, and some I/O devices. So these are the traditional conception about the digital computer systems. Now, when we are trying to make analog systems, like analog computing element, then we also need analog signal processing system or analog processing systems, then analog memory and I/O. Okay, analog memory already we have discussed, storing the information. using the floating gate transistor, we can store the informations, or using the transistors and some capacitors also we can design. Now, the question is, if we want to make a central processing unit, analog central processing unit, here also exactly the similar thing, similar data transfer mechanisms has to be adopted. So once the transfer of data will take place, we need to store the data. In digital, we have the registers where the data can be stored in the bit form. For 8-bit data storage, we can have 8-bit registers. Each register is 1-bit storing device, okay, which can be designed using latch. But again, the question comes, how the data will be stored in the analog? So anybody can answer to these questions? Because we are going for analog digital signal processors. So how this data will be stored? Instead of register, how the registers can be implemented for analog device? Think and tell, it should not take time.
So using floating gate,
Using?
so using floating gate transistors.
Okay, you can use, but don't you feel that capacitors will
Yes, sir. Yes, sir. The analog memory.
analog memory? The data can be stored in the capacitor in a simple way. We don't need much more device, because now you compare. Say, if you sample the analog signal, okay, each sample, if you convert it to digital, so at each point, the sample data will consist of 8-bit or 16-bit or 32-bit, something like that. That means that many number of storage elements will be required. Now, each data, each bit consists of how many bits to store in digital form? Each bit of information will be requiring. Tell me.
Sir, please repeat, sir. Last line.
Each bit of information, digital information, if you want to store, how many transistors will be required?
Sir, 6.
Okay, good. 6 transistors will be required. Now, only 6 transistors will not help. Along with that, some resistors and all has to be there, isn't it? Something like that. If you use CMOS, perhaps resistance will not be required. Straightaway you can connect them. But 6 transistors will be required. Now, each data,
Yes.
each sample, the analog sample data, if you want to store, how many elements will be required? Tell me. What is this? Can't you store like that? This is a circuit. Okay.
Yes.
If I give a simpler circuit, let's say, this circuit stands for what? For storing of what? Analog cell? Isn't?
Yes, sir.
Now here, which is more complex, this one or your SRAM? Digital or analog?
Analog.
Analog is simpler, isn't?
Yes. Sir.
Even further, we can simplify these things by using only 2 transistors. Also, you can do that. That's not a big deal. Okay. Like one will be writing the data by controlling it, another is reading the data from here. Simple thing. So one thing is very clear. Now, do you have any questions? Why analog is simpler than digital?
No, sir.
Like the questions will come like that. What are the basic elements for storing the data in analog? What is your answer?
Sir, capacitor and
Capacitor.
transistor.
Capacitor. Why transistors are required? Because to control
Sir,
the write
for
or read
the
operations.
switching purpose. Yes, sir.
For read or write operations, we have to use some control, and that's why we use the transistors. But overall number of transistors and capacitors, considering the complexity, will be less, much less compared to your digital counterpart. It's okay. Now, now we'll discuss so our next topic of discussion is analog signal processing. Can we take some time, some 5-10 minutes? Hello?
Yes, sir.
Okay, sir.
Okay.
Yes, sir.
Now for signal processing, the basic building blocks are adder, subtractor, multiplier, and delay. We know that in digital signal processing, we learned these things. So this is addition to, now here the signal in the discrete form will be denoted by n, xn. Okay. Xn, n is the sampling number. And delay will be denoted as z to the power minus 1. And this is multiplier. But this multiplier is a multiplication by a constant. Okay, so it's basically an amplifier. If A is the gain, Xn is the input and Yn is output, then Yn will be A into Xn. Okay, so that is a basic concepts. Now I want 1 second. Let me bring. And you know this continuous time signal will be sampled to get the discrete values like x0, x1, x2, etc. Now again, reviewing the switched capacitor circuits. So now using this circuit, this is a circuit for what? If you look at this circuit can function as what? Is a scale changer or integrator or differentiator or multiplier?
Sir, integrated circuit.
Integrator.
It's an integrated circuits. Okay. So first, these switches. So initially it will be like that. If we see that at, let's say at, if I say that at n minus 1th instant, clock phi 1 is on and phi 2 will be off. When phi 1 is on and phi 2 is off, the equivalent circuit is like that. Can't I say this? The upper one.
Yes, sir.
So what will happen to this circuit? What is going to do? At when the phi 1 is 1, at let's say at n minus 1th instant, what is going to happen? Anybody? A voltage
Sir,
V1,
capacitor will be charged.
capacitor will be charged. You should save first, it should not take time. Capacitor will be charged. That's simple. And when next instant means initially we were defining n minus 1th instant, so now it will be nth instant. In nth instant, let's say phi 1 is off and phi 2 is on. So what is going to happen? Equivalent circuit is like that, isn't it? C1 was
Yes, sir.
already charged, and in that condition, this is. So this is the two diagrams. Okay. So during phi 2, so total charge on C1 and C2 during phi 1 will be the same in phi 2, because the charge cannot be, is a conservation of energy. Because charge is nothing but can be converted to energy. So total charge, you can say that during phi 1, when phi 1 is on, total charge on C1 and C2 will be same when phi 2 is on and phi 1 is off. Agreed?
Yes, sir.
Yes, sir.
Now what is the total? What is the charge? Total. So what is the charge when phi 2 is off and phi 1 is on? So can't I say that initially V1 N into C1, Q equal to C into V minus V0 N into C2? Consider this. At n minus 1th instant, what is the total charge? What is the total charge in C1 and C2? Yes. Say something. What is the total charge?
Sir, C into V.
What is C into V? How many capacitors are there? Tell me. You just look at the diagram, top diagram, at the right hand side. How many capacitors are there?
2 C1 and C2.
C1 and C2. So, what is the voltage at the output? What is the voltage at the output? What is written here?
V naught. V naught.
V naught. And what is the voltage at the input?
VI.
VI. So, what is that? What is the charge on the capacitor? C1.
Q is equal to C1 VI.
Okay. And what is the voltage? What is the charge on C1, C2?
V naught into C2.
That is positive or negative? It will be
Negative.
So in the negative direction. So total charge is, I can say that V1 in into C1 minus V2N into C2. Can't I say that? You understand
Yes, sir.
why it is minus? Because the output will be 180-degree phase from the V1. So if V1, if you consider it is positive, that will be negative. It's simple. Q equal to C into V. So C2 into V naught N. That is equal to, now consider the second diagram. In the second diagram, what is the total charge? What is the charge? C1 and C2. This is the diagram.
Sir,
Solve this
minus
diagram.
V naught into C1 plus C2.
So 1 is 0 into C1 because C1 will be discharged. It is connected to the ground. So it will be totally discharged. So 0 into C1
Yes, sir. Yes, sir.
minus V0 into N plus 1 into C2. Why I am calling it N plus 1? This is in the next instant. These are discrete systems.
Okay. Yes, sir.
This
Yes,
was in
sir.
the first instant. Okay, if I call it nth instant, then this will be N plus 1th instant. If I call it N minus 1th instant, then it will be nth instant. So let's say here we have said VIN into C1. That means in nth instant, the voltage into this capacitor minus V0 into N into C2. That will be equal to 0 into C1 minus V0 into N plus 1 C2. It's simple. Okay, that means total charge in phi 1 is equal to total charge in phi 2. Now you take Z transforms in both the sides. What is the Z transforms of VIN? That is VIZ, VIZ into C1 minus V0 Z into C2 equal to this. Simple thing. That means if we just simplify this will be C1 by C2 Z to the minus 1 by this. This is the equations. And from here you can find out. Similarly, we can take this kind of circuits. We can find out. And if we take these circuits by switching on and off, we can find out Hz equal to C1 by C2 into Z to the minus 1. That is a tensor function in Z domain, which is very important. And so what we can do, we can easily find out if we know Hz, that is a tensor function, then easily we can find out what is the value of Z to the minus 1 equal to how. So delay unit can easily be implemented by Z to the minus 1 equal to C2 into Hz by C1. So C2 by C1 is the ratio of the capacitors and Hz is the transfer function. That also can be known. So in that way, analog delay Z to the minus 1 is nothing but one delay unit can easily be implemented using switched capacitor circuits. Now, if we know these things, then digital filter structure. Do you remember this?
Yes, sir.
This Yn equal to Hk into Xn minus k. Hk is the impulse response. So multiplications and addition can be implemented easily by these structures. Already I've discussed these things. So some adder, multiplier, and delay units. So now multiplier you can easily implement. These multipliers are constant coefficient multipliers. Okay, there are two types of multiplications. One is two time domain functions are getting multiplied, which is nothing but modulation. Okay. And one is multiplications of a function by a coefficient, a constant. So here we require that because HKs are constant. These are impulse responses. So already we have shown that using switch capacitor, we can make multipliers, such multipliers. We can make delays, and we can make these analog signal processing systems. Now, these multipliers can be useful for making the neural networks also. So that we'll be discussing in the next class. Now, if you have any questions, please make it clear. So slowly we are going for making the digital analog signal processing systems, which we'll start discussing in the next lecture.